So for start, you're going to copy the concepts, key concepts on page 436, and then we're going to go back and we're going to look at one of the diagrams on page 429. So if we're going to graph the first one, the first point is 2, 5. So we can go to 2 and to 5, and that is your first position vector. Okay, we just had the point, but we can say it as a position vector. The second one is 4, 1. So there's your second one. So if we want to find the one that we are looking for the one that goes between these 2 points. Now, the direction I have it going up, down, ultimately at this point, the direction doesn't really matter because lines always extend in either direction, right? This is an equation of a line, like y equals mx plus b. But currently, this is the direction vector. This is what we're solving for. So that O simply just means it's the position vector and it's coming from the origin. And we just subtract our B point, which is 4, 1, from our 2, 5. And this will get you the vector, which is parallel to our direction vector. So if we're going to write this total, we're asked for the entire vector equation. Right now we have x, y, which we don't put anything in, just like in y equals mx plus b. We don't have numbers in the y and we don't have numbers in the x. They're just left blank. And then we have x naught and y naught plus t times our m, which we just found. The other part to this that we still have to fill in is the x naught, y naught. The xy still stays as is. And for that x naught and y naught, you can pick any point that is on that line. So any point meaning either B or A, doesn't matter. So we'll just go with the first one. We'll go 4, 1. And then you have plus t times 2, negative 4. So any point along that green line. So let's say pick any t value. What t value do you want? We can pick a t value of 5. So if we sub that in, we have x, y equals 4, 1 plus 5 times 2, negative 4. So that would be your final position vector of 14, negative 19. And so for part C, when you have to write it as a parametric equation, you just take your vector equation and you write it as the components. So just your x part is back up to here, 4 plus 2t, and your y component is 1 minus 4t. Now, this part will be different depending on the point that you picked, but it really doesn't matter which point you pick because you know that both of these still lie on that line. So if you want to see another example of this, you can look on page 432, example number 2. So our first part, given this standard form or scalar form, we have to graph it. There's different ways that we can graph this. What's one way you can graph the line given that scalar? Yep. Good. You can use x and y intercepts and then just connect the dots. That's perfect. What else? Yep, James? So yeah, you can rearrange it into this form. Once you have it into this form, how do you graph it? Once you have it in y equals mx plus b, what do you start with? Yep, you start with the y-intercept. From that y-intercept, what do? Yeah, you do your slope. So you rise and run from that y-intercept, and then you just connect those two dots. So for the x-intercept, what do you set equal to 0? The y. So if the y is 0, we just have 2x plus 30 equals 0, which then x equals negative 15 if you solve that. And then for the y-intercept, if you're looking for the y-intercept, you set the opposite one, x equal to 0. So you have negative 3y plus 30 equals 0. So y equals 10. Doing it the other way, rearranging, we're going to take everything to the right-hand side that's not y. So if it has a y, it's staying. So we leave negative 3y equals negative 2x minus 30. Then we have to divide each thing by the coefficient because we want it to just say y. So then we're left with 2 over 3x plus 10. So that would be your line using the x and y intercepts. So in order to get that position vector, you have to have the vector equation. And to do the vector equation, to get the m, what do you need? You need 2 points, which then makes it easier because we now have the x and y intercepts. So that's how we would have set it as coordinates. And if you do the subtraction, you have 15, 10 as your m. And when you write your equation, you need any point, doesn't matter which one. We'll go 0, 10 plus t times 15, 10, where t is any real number. So there's your vector equation. So since we now know this slope, right, the part that we're going to be perpendicular to, we can take this vector, 15, 10, and we can dot it with any vector. We don't know what it is. We're just going to call it xy and set it equal to 0 because we know that the dot product of two vectors, if it equals 0, that means it's perpendicular. And that's what we're looking for, the perpendicular vector. So we're going to keep solving this after the dot product, and you have 10y equals negative 15x. We're going to divide by 10, divide by 10. And to write it in lowest terms, we're going to write negative 3 over 2x. What would be an easy or more simple case to pick for that x? So if we're going to pick an x value, what would make this work out nicely? What x value? So we'll pick 2 because then we can see that if we make negative 3 over 2 times 2, what are we left with? Just negative 3. So a normal, which a normal is a perpendicular vector to your vector or to your line. A normal that we can have, in this case, we chose 2 and negative 3. And now I want you to notice the equation that we started with, and then a normal that we just found using the dot product. And what do you see? So you can see here that the x and the y component are the same components for your normal vector. So this is all the exact same in 3 space. You just have that extra component. So if you want to see an example that's in 3 space, page 434, example number 4 is an example of that.